A transformer can keep about the same language model quality while sending only a small chosen set of tokens through some attention and feed-forward blocks. The remaining tokens skip those blocks, making each forward pass much cheaper. Start with a sentence split into tokens. Each token becomes an embedding, a vector that carries the model's current information about that token. The full sequence then enters a stack of transformer blocks. In a normal block, every token goes through self-attention and then a feed-forward layer. Residual connections add each new result back to the token's previous embedding, so information can move safely through many blocks. The expensive part is uniform. Every token uses attention and the feed-forward layer at every depth. A simple word, punctuation mark, and difficult technical term all receive the same amount of processing. The new architecture places a router before selected transformer blocks. A router is just a small learned linear layer. It looks at each token embedding and decides how useful another full block of processing would be. For every token, the router produces one number. A larger score means spend attention and feed-forward compute on this token here. A smaller score means let this token skip the block unchanged. Before training, we choose a fixed number k, exactly how many tokens each routed block may process. The paper calls this the block's capacity. For 8 tokens, k could be 2. The router scores all 8 tokens, sorts those scores, and selects the top 2. Which 2 are selected can change with the sentence and with the layer, but the number 2 stays fixed. The selected token embeddings are gathered into a smaller fixed-size batch. That detail matters. The model makes a dynamic choice about token identity while the hardware always receives the same amount of work. Only the selected tokens enter self-attention in that routed block. They form the queries, keys, and values, so attention is computed over the smaller selected set instead of the complete sequence. After attention, the same selected tokens pass through the feed-forward layer. This is the other large computation inside a transformer block, and skip tokens avoid it completely for this layer. For a selected token, the block's new output is multiplied by that token's router score and added to the residual path. This also lets normal language model training teach the router which choices are useful. Every unselected token takes the cheap path around attention and the feed-forward layer. Its embedding is copied forward through the residual connection, so skipping a block does not delete the token. Processed and skipped tokens are placed back into their original sequence positions. The next normal transformer block receives a complete sequence again, with the same length and token order as before. At the next routed block, a new router scores the updated embeddings again. A token that skipped one block can be selected later, while a previously selected token can skip the next one. That creates the mixture of depths. Different tokens pass through different numbers of attention and feed-forward blocks, even though they remain inside one shared sequence from input to output. This is not early exit. Early exit permanently stops processing a token after some layer. Here, a token can skip a middle block, rejoin the sequence, and receive deeper processing later. Because every routed block always selects exactly k tokens, its input shape is known before the model runs. Total compute is predictable, even though the actual selected tokens depend on the current sentence. A common router lets each token choose a destination, but too many tokens may crowd into one path. This design reverses the choice. The expensive block chooses its top k tokens, guaranteeing a fixed workload. The final routing rule is therefore simple. One path contains self-attention plus the feed-forward layer. The router sends the top k tokens there, and every other token takes the residual shortcut. There is one complication during text generation. Training can find the top k scores across a complete sequence, but generation sees only the tokens written so far. Future router scores do not exist yet. The paper trains a small helper to predict whether the current token would have entered the top k. During generation, that local prediction replaces the full sequence ranking and enables causal, one token at a time, decoding. The experiments compare normal transformers with routed models under the same total training compute. Model sizes range from 60 million to 3 billion parameters, with sequences of 2048 tokens. Their strongest small-scale setup routes every other block and processes only 12.5% of tokens inside each routed block. Full blocks between them let every token regularly exchange information. In one 220 million parameter comparison, the routed model reached slightly better training loss while stepping about 66% faster. During later text generation, some models were up to 50% faster. Skipping is not free of consequences. A skip token is also absent as a key and value in that block's attention, so the router must consider how today's choice affects later tokens, not only the current prediction. The full mechanism is score every token, select a fixed top K, run those tokens through attention and the feed-forward layer, copy the rest through the residual path, merge the sequence, and repeat at a later depth.